Namaskaram. Welcome to series of lectures on finite element method. In previous class we discussed about strain displacement matrix for two-noded 1D bar element. Today we will discuss about stiffness matrix for two-noded 1D bar element. In previous class we derived in important parameters. One is displacement, which is nothing but n1 q1 plus n2 q2. So in essence I can write this displacement is equals to nq, and we derive the strain du, that's nothing but bq, where b is the strain displacement matrix, and we know the relation between stress and strain, that is stress is equals to d into epsilon, where this d is basically material property matrix. Material property matrix. And suppose if you are considering one-dimensional element, then this d will become the Young's modulus, which is only the material property. It is for 1D element. So I can write this stress is equals to E into strain, and essentially I can write this one is equals to E into B into Q. This is for 1D element, and in general this equals to D into B into Q for 2D and 3D elements. And if it is a 2D element, then this D, the material property matrix, will be your 2 by 2 matrix, and if it is for the 3-dimensional element, that will be the 3 by 3 square matrix. That we will see in further lectures. So but today the essential focus is that we are considering only one-dimensional elements. That's why essentially we will get this stress as EBQ. Right. So this way we got the three important expressions. One is your displacement, U is equals to NQ, where N is actually shape function matrix, and second one is your strain, which is nothing but BQ, where B is your strain displacement matrix, which we discussed in previous class. And stress, which is nothing but your EBQ. So these are the three important parameters we need. And once we have these parameters, then to find out the stiffness matrix, either you can use the approach of potential energy or by using Galerkin methods. The potential energy is actually applied by Rayleigh-Ridge. So that means Rayleigh-Ridge method can be applied by using the potential energy or by the Galerkin's approach, which uses the virtual work. So today the focus is mostly on by using this potential energy. We already discussed the potential energy in a given object when it is subject to the different boundary and load conditions is equals to U plus W into P, where U is nothing but your strain energy and WP is actually your work potential. U strain energy and WP is basically your work potential. So work potential, it is actually the work done against all the external forces. Work done against all external forces acting on the system. Right. So we try to use this potential energy to find it out the stiffness matrix for 2 noded 1D bar element. So if you write this potential energy phi U into work potential, this U is basically of volume integral of sigma transpose into epsilon naught into dV. And work potential, it is work done against all the forces, that's why you'll have all the negative values of it. So volume integral of U transpose into F of dV minus of surface integral of U transpose into T into ds and summation of all point loads, that is Ui transpose into Pi. We have discussed all these terms detailedly in previous classes. Just for a recap, where sigma is actually the stress and strain, and F is basically the body force, that is force per unit volume, and T is actually the traction, and Pi's are actually the point loads acting at different positions. Now whatever the expressions we have already, we have U, which is nothing but your NQ, and strain epsilon naught is nothing but your BQ, and your stress, which is nothing but your dBq. It is a general dBq method, right? If it is a one dimension, you can write it as E also. So I want to put it in a general form, then you can substitute that E, we can replace D with E. So these are the three which we have, and we will substitute all into this potential energy expression, right? So when we substitute them, we will get here sigma. So sigma transpose means how we can write here? Sigma transpose is nothing but, so you'll have this D into Q transpose into B transpose, because D is actually the material property which is constant, it doesn't change. So you'll get this and BQ, and U transpose, you can write that one as Q transpose into N transpose. So you can substitute all these values into our potential energy expression of volume integral sigma transpose, that is nothing but D into Q transpose into B transpose, and into epsilon naught, nothing, that is that B into Q into dV, and volume integral of U transpose is nothing but Q transpose into N transpose into F into dV minus of surface integral Q transpose into T into ds and sum of all the forces acting at different points. Those are all point loads. You can write this expression this way. Now this part is basically your strain energy. This part is basically your strain energy, and these all are actually forces. So when you consider the strain energy, from the strain energy you will get an expression, that is your stiffness matrix. Whereas from these loads we will get the different forces, so we call them as force vectors. So these force vectors will have, one is like a body force, so you will get a body force vector, and you will have another like tractions, that means they are surface forces, and you have point loads. Because this one expression, this expression will give you the body force, and this expression will give traction, and this one will give you point loads, right? So now we'll consider this first term, that is the strain energy, and we'll try to find it out, the stiffness from the strain energy. So I'll write just a strain energy in that element. So the strain energy is element, right? That is, let me take U, E, So I am writing this expression as UE. So that's nothing but of volume integral of, what was the expression we have? Volume integral of d q transpose bq into dv. So d q transpose into b transpose into b into q into dv. Right. So now since we are considering the one dimensional element, I can write this volume of the element in terms of the a into dx, because now the variation is happening only in x direction. If you are considering this element, so the deformations are forces all are acting in one direction, that is in the x direction. So I am converting this volume dv in terms of a into dx. So then I can convert this volume integral into over the length of this element. So I can write this expression as 1 into over the length to d q transpose v transpose v into q to a into dx, where a is the cross sectional area, and I already told in the previous class. So within this element the cross section is same, so that means it is constant over the element, right? So d is a material property which is again a constant, and q is basically your displacements at a particular nodes, so they are also constants. So if I rearrange this term, I can write them as of d a and this q transpose into, it is over the length. So we know if you are considering this length, if it is x1 and x2, so this length, suppose I am considering this x1 is 0, then x2 will be my LE, means the length of the element L. So that means it's varying from 0 to L, 0 to L, right? 0 to L, and I have an expression B transpose into B into dx into q, right? So if I can rearrange these terms in a proper way, then I can write this one as of q transpose into d into a 0 to L b transpose into b to dx into q. And if you can recollect our previous class studies, we can write strain energy in a spring. Strain energy in a spring, right? That u, strain energy in spring, is nothing but of k q square, or sometimes we'll write it as of k x square, because mostly in your school or in high school you must be used as x term. So of k x square, and what are this k? K is basically your stiffness and x is basically your displacement. And if you can correlate that expression which we have here and this one, so both are similar. So if you can observe it, this entire term which we have, right? And if you can see this term k, right? So this x square and this q transpose and q is nothing but, q is again displacement, right? And when it is in a matrix form, then if you want to multiply, you have to write it in q transpose and q. So this q is reflecting as a displacement x and again q. So that x square is nothing but is q transpose and q, and the rest this k is nothing but this k, right? So we can write this now that this entire strain energy u is nothing but of q transpose into ke into q, where this ke is nothing but element stiffness matrix, right? Element stiffness matrix. What is that you have in that? You can see that is having dA, so integral of 0 to L and B transpose into B into dx. B transpose into B into dx. So this is an important expression. This is very an important expression. I'll write it in a better way also, because here this dx I converted. If you don't convert it, it is simply, it is in the form of like this d. Let me put them all in n. So 0 to L d into B transpose into B into A into dx means it is a dV. So it is a standard stiffness matrix. So that is of course when I am taking the volume here, it should be again for the volume rather than this, it should be for a volume. So I'll rewrite in a for element stiffness matrix, that is equals to for a volume integral d into B transpose B into dV. So it is applicable whether it is a 1 dimension, 2 dimension or a 3 dimensional as well. Only thing is that based on the number of dimensions in the element, this d will change and your B will change, right? So d, for if it is for 1 dimensional, the d will be just simply a E. If it is for 2 dimensional, the d will be of 2 by 2 matrix. Generally we have an expression for the plane stress values. We will have something like E by 1 minus nu square into 1 nu 0 nu 1 0 0 0 1 minus nu by 2. So that way you will get 2 by 2 D matrix. Again for 3 dimension you will have 6 by 6 matrix. So to find out the stiffness of the matrix, whether it is a 2D or 3D, what you have to do, you have to know what is the D matrix, right? You will know that, and you have to know your B matrix. That's why previous class we discussed about strain displacement matrix. So this B is nothing but what? This B is nothing but your strain displacement matrix. Matrix. So this is the general expression for any stiffness matrix. Now since we are talking about to find it out the stiffness matrix for the 2 noded 1D bar element, so now we will substitute them in 1D. So we got this expression Ke as volume integral of D into B transpose B into dV. This is a general expression. Now I am converting that one into a 2 noded 1D bar. So I'll get from 0 to length and d B transpose B into A into dx. And you know, if it is a 1 dimensional, I said this material property matrix D will become E. So it will become E. A is also comes out A, and 0 to L, and B transpose into B into dx. And we already derived what is the strain displacement matrix B, if you remember. So that we written as 1 minus L by 1 by L. That is our strain displacement matrix. So if you substitute here in this expression, then you will get EA and B transpose, that means 1 by L and again 1 by L. I'll get a form, and multiplied with minus 1 by L into 1 by L into dx integral over L, right? So if you write that expression, you will get Ke EA, and you will have this integral 0 to L, and if you write this expression, what you will get? You will get this one as 1 by L square or I can take it out. So let me keep this one 1 by L square. You will get this, and so this will become plus, and minus into this you will get minus 1 by L square, and again here you will have minus 1 by L square, and we'll have 1 by L square into dx. And you know this L is actually length of the element, so if we can take it out, you will get A by L square out. So you will have 1 minus 1 minus 1 1 into dx over 0 to L, right? So if you integrate it, what you will get? You will get that expression. If you integrate it, you will get this expression Ke is equals to A by E by L square. So you will have x minus x minus x x. You will have these 4 terms, and it should be to the limits of 0 to L. So if you get, you will get AE by L square. This you will get it if you put the terms here. You will have L, it is 0, so I'll have L minus L minus L L. If you take it out L, then I'll get AE by L equals to 1 minus 1 minus 1 1 is equals to Ke. So this is very important matrix to understand. That is your stiffness. So this is called element stiffness matrix. So since we have considered 2 nodes, so if you observe it, we got this element stiffness matrix as 2 by 2. And if you see what are the parameters you have in that, A, E, L. And if you see A and L, basically they are the geometry of a given element. E is basically your material property. So the stiffness matrix is a combination of your geometry as well as material property of a given material. Right? So that way we derived the stiffness matrix for 2-noded 1D bar element. And it is very important when we try to solve our problems in future lectures. So we derived stiffness matrix from this, and we have the previous 3 terms. If you here, so these forces, with these forces we'll try to derive our force vectors. So that I will continue in the next class. Thank you for your attention.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.